So today's lecture is a continuation of our previous lecture on ionization energies. So the lesson objective before us today is to identify and explain the trends in ionization energies across a period and down a group of the periodic table. As you go across the period that you go down the group, want to see the trend or the changes that takes place in the ionization energies or the force ionization energies of the elements as you go across the period and also as you go down the group. So we want to look at patterns in ionization energies in the periodic table. We want to look at the trend in ionization energy as you go across the period. So by looking at patterns across a period. Now, if you go as you go across the period, you can take period 1 or period 2 or period 3. As you go across the period, what happens is that the first thing you observe is that the atomic number increases. That means the number of protons increases. So that simply means the positive nuclear charge will increase. Another thing you observe is that all the electrons, all the atoms, all the electrons are on the same shell. So the number of shells remains reasonably constant. There's no change. The number of shells remains the same. And the shielding also remains the same. So as you go across the period, the number of protons increases, so the positive nuclear charge increases, the shells remains constant, the shielding remains reasonably constant. So the ionization energy increases as you go across the period. So these patterns can be explained by referring to factors that influence ionization energies. There's a general increase in force ionization energies across a period. Now this applies to all periods, whether period 1, period 2, period 3, period 4. So as you go across a period, the nuclear charge increases because the number of protons increases. The atomic number, which is the number of protons, increases, so the nuclear charge will increase. But the electron removed comes from the same shell. So the force of attraction between the positive nucleus and the outer negative electrons increase across the period because the nuclear charge increases. Then the distance between the nucleus and the outer electrons remains reasonably constant. That is, the number of shells remains reasonably constant. Then the shielding by inner shells remains reasonably constant. So the only thing that increases is the positive nuclear charge. The nuclear charge increases because as you go across the period, the number of protons increase, so the nuclear charge will increase. So ionization energy increases as you go across the period. The first ionization energy increases across the period. So we are looking at patterns across a period, the pattern of the force ionization energy across a period, the trend in ionization energy across the period, that as you go across the period, ionization energy increases across a period. So we want to look at the force and ionization energy of period 2 elements. So the graph before us is a graph of the ionization energy against Against atomic number of period 2 elements. So we want to look at the period 2 element. But we also have period 1 elements here, which are hydrogen and helium. Hydrogen and helium, they belong to the same period. They have the same number of shells. If you draw the electronic configuration, they have the same number of shells. But we want to look at the period 2 elements, which are lithium to neon. If you look at the period 2, from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So we want to look at the trend in the force ionization energy as you go across the period. Now the normal trend is that as you go across the period, ionization energy increases across the period because as the atomic number increases, so the number of protons increases, so the nuclear charge will increase. But the shells remain the same and the shielding remains reasonably constant. That means the ionization energy is supposed to increase. But if you look at from lithium to neon, there's a drop between beryllium and boron and nitrogen and oxygen. Under normal circumstances, the ionization energy of boron is supposed to be higher than that of beryllium because of the number of protons, because of the atomic number. Boron is 5, beryllium is 4. So the ionization energy of boron is supposed to be higher than that of beryllium, based on the trend that ionization energy increase across the period. But there's a drop in boron. Then if you look at nitrogen and oxygen, nitrogen is 8, oxygen is 8, and nitrogen is 7. So the number of protons of oxygen is more than that of nitrogen. That means the ionization energy of oxygen is supposed to be higher than that of nitrogen. So there's a drop. So we're going to look at the reason why there's a drop between beryllium and boron and nitrogen and oxygen. These are the only exception in period 2 elements. So, but the normal trend is what? Ionization energy increase across the period. So as you go across the period, for period 2 element, from lithium to neon, ionization energy is supposed to what? Increase. So the only exception is between beryllium and boron and nitrogen and oxygen, of which we are going to discuss it, and we're going to see the reason why there's what? A drop, why the ionization energy of boron is lower than that of beryllium, why the ionization energy of oxygen is lower than that of nitrogen. So looking at beryllium and boron and nitrogen and oxygen in period 2, there is a drop in the ionization energy. There is an exception to the trend, because the trend is that as you go across the period, the nuclear charge increases, so the ionization energy increases. But between beryllium and boron and nitrogen and oxygen, there is a drop. So we want to see the reason why the ionization energy of beryllium is higher than that of boron, why the ionization energy of boron is lower than that of beryllium. So there's a slight decrease in first ionization energy between beryllium and boron. Although boron has one more proton than beryllium, there's a slight decrease in first ionization energy on the removal of the outer electron. And the reason is simply because in beryllium, if you look at the electronic configuration of beryllium, it is 1s2, 2s2, and boron is 1s2, 2s2, and 2p1, because the atomic number of beryllium is 4, I mean to say, and that of boron is 5. So the reason is because in boron, the first electron is removed from a 2p subshell, and a 2p subshell is a higher energy subshell that is slightly further away from the nucleus than the 2s subshell. So there's less attraction between the electron and the nucleus. So less energy is required to remove the electron, resulting in lower ionization energy in boron. Then in beryllium, the first electron is removed from a 2s subshell, which is a lower energy subshell that is closer to the nucleus than the 2p subshell. So there's a greater attraction between the electron and the nucleus. More energy is required to remove the electron, resulting in a higher ionization energy. So that is the reason why there's a drop in ionization energy between beryllium and boron, that the ionization energy of boron is lower than that of what? Beryllium, and why the ionization energy of beryllium is higher than that of boron, which is a deviation from the trend that ionization energy increase across the period. So please, I want us to take note of that. Between beryllium and boron, there is a drop, and we have to know the reason for the drop. The reason for the drop is that in boron, the first electron is removed from the 2p subshell, which is a higher energy subshell, farther away from the nucleus. So it's easy to remove an electron from a higher energy subshell. But in beryllium, the first electron is removed from a 2s subshell, a lower energy subshell closer to the nucleus. So it's difficult to remove an electron from electron from a subshell that is closer to the nucleus. So the ionization energy of beryllium is higher than that of boron. So please, I want us to take note of this exception because it's very, very important. The next point where there is a drop is between nitrogen and oxygen, where the ionization energy of oxygen is lower than that of nitrogen, and the ionization energy of nitrogen is higher than that of oxygen, which is deviation from the trend in period 2. So looking at pattern across a period, so we see there's a slight drop, there's a slight decrease in first ionization energy between nitrogen and oxygen. Oxygen has one more proton than nitrogen, and the electron is removed is in the same 2p subshell. So you might think that the first ionization energy will increase, because as the number of protons increase, so the nuclear charge, positive nuclear charge increase, so the ionization energy is supposed to increase. But you know, that is a deviation from the trend. Now, if you look at oxygen, this is oxygen. Oxygen is 8. Oxygen is 8, atomic number 8, which is 1s2, then 2s2, then 2p4. So you have this 1, 2, 3. So you have 1, 1, 1, 1. Then this is nitrogen. I think we need to draw this for proper explanation. 1s2 is nitrogen, 2s2, then 2p3. So if you look at the electronic configuration of nitrogen and oxygen have one more proton than nitrogen. So the reason why the first ionization energy of oxygen is lower than that of nitrogen is because in oxygen, the first electron is removed from what? A paired orbital. The first electron is removed from a paired orbital, where a paired orbital where repulsion has taken place. In an orbital, electrons spin in opposite what? Direction. And these both electrons are negatively charged. So repulsion has taken place between what? Between the electron. So the first electron is removed from what? A paired orbital where repulsion has taken place. So less energy is needed to what? Remove what? Remove the electron. So the first energy of oxygen is lower. But compared to nitrogen, in nitrogen, the first electron is removed from what? An unpaired what? An unpaired orbital. So it's easy to remove an electron from a paired orbital compared to what? An unpaired orbital. Because in a paired orbital, there's what we call spin pair repulsion. Since electrons are both of them are negatively charged and they spin opposite direction, so repulsion has already taken place. So you need less energy to remove the electron in a paired orbital in oxygen compared to nitrogen, where the first electron is removed from what? An unpaired what? Orbital. So that is why the ionization energy of oxygen is lower than that of nitrogen, and the ionization energy of nitrogen is higher than that of oxygen. So, however, the spin pairing of the electrons plays a part in the ionization energy of oxygen and nitrogen. The electrons removed from oxygen is from the orbital that contains a pair of electrons. The extra repulsion between the pairs of electrons in this orbital result in less energy being needed to remove an electron. So the first ionization energy for oxygen is lower because of spin pair repulsion. While in nitrogen, the electron is removed from an orbital that contains an unpaired electron. So it is easier to remove an electron from a paired orbital as a result of spin pair repulsion compared to an unpaired orbital. So that is why the ionization energy of oxygen is lower than that of nitrogen, and the ionization energy of first ionization energy of nitrogen is higher than that of oxygen. So please, I want us to take note of this. It's very, very important. So still on pattern across the period. So we're looking at the trend in ionization energy across the period. So I want to look at first ionization energy of period 3 elements, which are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. So the graph before us is a graph of the first ionization energy of the period 3 elements and the elements or the atomic number of the element. So if you look at the graph, you discover that as you go across the period, ionization energy increases across the period going by the normal trend. But there's a deviation, there's a drop in ionization energy between magnesium and aluminium, and phosphorus and sulfur, which are deviation from the trend. The ionization energy of aluminum is lower than that of magnesium, but going by the trend, ionization energy of aluminum is supposed to be higher than that of magnesium, because aluminium, the atomic number of aluminium is 13, while that of magnesium is what? 12. The same thing with phosphorus and sulfur. Ionization energy of sulfur is lower than that of phosphorus. It's supposed to be higher than that of phosphorus, going by the trend that ionization energy increase across the period. So these are exceptions. The two exceptions is between what? Magnesium and aluminium, then phosphorus and sulfur. So we're going to look at the cause, the reason why the ionization energy of aluminium is lower than that of magnesium, and why the ionization energy of sulfur is lower than that of phosphorus. So considering period 3 elements, there is a deviation from the trend between aluminium and magnesium. So we want to see why the first ionization energy of aluminium is lower than that of magnesium, or why the first ionization energy of magnesium is higher than that of aluminium. So there's a slight decrease in the first ionization energy between magnesium and aluminium. Yes, although aluminium has one more proton than magnesium, there's a slight decrease in the first ionization energy on the removal of the outer electron. Now, if you look at the electronic configuration of magnesium, it's 1s2, 2s2, 2p6, 3s2. and that of aluminium has the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p1. So in aluminium, what happens is that the first electron is removed from a 3p subshell, which is a higher energy subshell, farther away from the nucleus. So it's easier to remove an electron from what? From a higher energy subshell. So the ionization energy of aluminium is lower than that of magnesium. While in magnesium, the first electron is removed from what? A 3s subshell, which is a lower energy subshell closer to the nucleus. So more energy is needed to remove what? The electron. So just as we have here that in aluminium, the first electron is removed from a 3p subshell, a higher energy subshell that is slightly further away from the nucleus than the 3s subshell. So there is less attraction between the electron and the nucleus. So less energy is required to remove the electron, resulting in a lower ionization energy for aluminium. But in magnesium, the first electron is removed from a 3s subshell, a lower energy subshell that is closer to the nucleus than the 3p subshell. There's a greater attraction between the electrons and the nucleus. More energy is required to remove the electron, resulting in higher ionization energy. So the first ionization energy of magnesium is higher than that of aluminium, and the first ionization of aluminium is lower than that of magnesium. So it's as simple as ABC. Please, I want us to take note of that, because those are the basic exception in period 1. In period 3, it's just the same explanation. In period 2, you have a drop between beryllium and boron. The same thing with magnesium and aluminium. So going across the period in period 3, the first ionization energy of sulfur is lower than that of phosphorus. That means there's a drop, there's a deviation from the trend between phosphorus and sulfur. There's a drop in ionization energy as you go across period 3 elements. You know, the normal trend is that as you go across the period, ionization energy increases across the period as a result of increase in the number of protons, which results in increase in the positive nuclear charge. Sulfur have one more proton than phosphorus. So the ionization energy of sulfur is supposed to be higher than that of phosphorus, but the ionization energy of sulfur is lower than that of phosphorus. So the reason is because if you look at the electronic configuration, the atomic number of phosphorus is 15. Number of phosphorus is 15, while the atomic number of sulfur is 16. So if you are to draw the electronic configuration, let me use this neon. So you have 3s2, then 3p3, then for sulfur, then you have 3s2, then 3p4. So if you are to draw the orbital box notation for the outer of 3p, so you have 1, 1, 1 going by Holmes rule. You fill singly before you start pairing. Then you have 3p4. So you draw the electronic configuration. So you fill singly 1, 1, 1, then before you start pairing. So you can see that the first ionization energy of sulfur is sulfur. This is an electron, negatively charged, negatively charged. So in sulfur, what happens is that the first electron is removed from what? A paired orbital, where repulsion has taken place. You know, since both electrons, in an orbital, there are electrons, and both electrons are negatively charged, so they've repaired themselves already. So less energy is needed to remove the electron. So that is why the first ionization energy of sulfur is lower than that of phosphorus. In phosphorus, the first electron is removed from what? An unpaired orbital. So more energy is needed to remove an electron from an unpaired orbital compared to what? A paired orbital, as a result of spin pair repulsion. So if you look at sulfur, that the ionization energy of sulfur is lower as a result of spin pair repulsion that has what taking place. So there's a slight decrease in the first ionization energy between phosphorus and sulfur. Despite the fact that sulfur have one more proton than phosphorus, the electron removed is in the same 3p subshell. So one might think that the first ionization energy would increase. However, the spin pairing of the electrons plays a part here. So the electron removed from the sulfur is from the orbital that contains a pair of electrons. The extra repulsion between the pair of electrons in this orbital result in less energy being needed to remove an electron. So the first ionization energy for sulfur is lower than that of phosphorus because of spin pair repulsion. While in phosphorus, the electron is removed from an orbital that contains an unpaired electron. More energy is needed to remove an electron from an unpaired orbital compared to what? A paired orbital in sulfur as a result of what? Spin pair repulsion. So the force energy of sulfur is lower than that of what? Phosphorus. And the force energy of phosphorus is higher than that of sulfur. This as a result of what? Electron being removed from an unpaired orbital in phosphorus, where more energy is needed, compared to what? Sulfur, where spin pair repulsion has taken place, where less energy is needed. So we want to look at patterns in ionization energy as you go down the group. Patterns down a group. What is the trend in ionization energy as you go down the group? Now, if you look at group 1 or group 2, as you go down the group, the first thing you are going to observe is there's an increase in atomic number. As you go down the atomic number increases. And atomic number is the number of protons, so the number of protons increases. That means the nuclear charge will increase, the positive nuclear charge will increase as you go down the group. So ionization energy is supposed to increase as you go down the group. But if you look at the distance between the nucleus and the outer electrons will increase, the shading by complete inner shells will also increase. So you can see that these two factors will outweigh the effect of the positive nuclear charge, despite that the nuclear charge is increasing down the group. But the distance between the nucleus and the outer electrons will increase. The shading by complete inner shell increases. So these two factors outweigh the increased nuclear charge. So these two factors will outweigh the effect of the increased nuclear charge. So the force energy decreases as you go down the group. So the force energy decreases as you go down a group in the periodic table. The reason is because as you go down the group, the outer electrons removed is from the same type of orbital, but from a successively higher principal quantum level. 2s from lithium, 3s for sodium, 4s for potassium. Although the nuclear charge is increasing down the group, there is less attraction between the outer electrons and the nucleus, because the distance between the nucleus and the outer electron increases, the shading by complete inner shell increases. So these two factors outweigh the effect of the positive nuclear charge. So the ionization energy decreases as you go down the group. So based on what we've treated, based on what we've done, these are exam style questions for us to attempt. Now let's look at this question together. The first ionization energies of 4 consecutive elements in the periodic table are sodium 494, magnesium 736, and aluminium 577, silicon 786. So if you look at the elements, you discover that they have the same shares, the same shading, so you are going across the period. So what they're just trying to ask here is that the first ionization energy of 4 consecutive elements in the periodic table are shown. So they're trying to ask you to explain the general increase in ionization energy from sodium to silicon. That means they're asking us to explain the general increase in ionization energy across a period, because from sodium to silicon you are going across the period. So as you go across the period, what happens from the figures given here, from the values we have here, the ionization energy increases as from sodium to silicon. That is going across the period. Ionization energy increases because the nuclear charge will increase as a result of increase in number of protons. So what happens? The shells remain the same, and the shading remains reasonably constant. Then the next question is explain why aluminum has a lower force ionization energy than magnesium. Aluminium have a lower force ionization energy than magnesium because in aluminium the first electron is removed from a 3p subshell, higher energy subshell, which is further away from the nucleus, so less energy is needed to remove the electron, compared to magnesium, which is removed from a lower energy subshell, which is 3s subshell, which is a lower energy subshell closer to the nucleus, where more energy is needed to remove the electron. So it's as simple as ABC. So I advise you to attempt as many questions as possible, and feel free to reach out to me if you encounter any difficulty. Please, I want you to subscribe to my YouTube channel, comment, like, share, and reach out to me. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. So this is a task for us to attempt. Successive ionization energy for the elements magnesium to barium are given in the table. Explain why the first ionization energy decreases down the group. So please, I want you to attempt this task and solve as many questions as possible. Attempt as many questions as possible and reach out to me if you encounter any difficulty, if there's any area of confusion. Just feel free to reach out to me. Subscribe to my YouTube channel, comment, like, share. So please, I want us to attempt this question. I'm Mr. Joseph, your chemistry teacher. Feel free to reach out to me if you have any difficulty. I'm always there for you. Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel. Thank you for listening.